All right, so we'll start off with the exponential function. All right, so okay, so we'll start off with the definition of the exponential function. Okay, all right, so here we go. And an exponential function is a function of the form okay, so it looks like this. It's f of x equals b to the power of x, okay? And there are some conditions on the base of the exponent, so let me just state those, where b is greater than 0, but it's also not 1, okay?
Hi, Mr. Roberts.
Hey, Saeed, how you doing?
Good, how are you?
Good. All right, so that is the definition of an exponential function. So the variable is in the exponent, and b is just fixed, okay? It's just going to be some number that's greater than 0, but also not 1. All right, so that's an exponential function. So just two very quick examples of exponential functions. So one of them would be when the base is 2. So how about 2 to the x? That's a good old exponential function. Okay, so just notice that the base is constant. Like the base is staying the same no matter what x value I plug into the function. It's the exponent that is varying. Okay, that's where the variable is. It's in the exponent. Okay, so this is a different story than a polynomial, where the variable was in the base. Okay, and just one more example. How about f of x equals, how about 1/2 to the x power? All right, so these are just examples of exponential functions. All right, so I hope that's cool. All right, so let's just graph one of these guys. Okay, so let's graph actually 2 to the x. Okay, let's graph y equals 2 to the x, and we'll do so just by making a function table. All right, our good old function tables. Make a function table. All right, so recall to make a function table, you just want to pick some nice values of x to plug into your function. So I think we're all very familiar with how function tables work now. We've worked with them extensively over the last few weeks. Okay, so the x values I will choose to input into my function, I'll just go from -3 to +3, the whole numbers in between. So we'll do -3, -2, -1, 0, 1, 2, 3. All right, so let me plug these numbers in the top row, the x values, into the function 2 to the x. All right, so 2 to the -3, that will be 1/8. 2 to the -2 will be 1/4. 2 to the -1 will be 1/2. 2 to the 0 is 1. Okay, now we're moving into these positive x values. We'll do 2 to the first power, which is 1, 2 to the second power, which is 4, and 2 to the third power, which is 8. Okay, so is anyone confused how I got these values in the bottom row here? All right, so we have to call upon our rules for negative exponents that we did in the beginning of the semester. All right, so I hope everyone's okay with how I obtained the outputs. the bottom row, which are the outputs. Okay, good. So what you would do in practice is now you would plot these XY coordinate pairs and then kind of draw a smooth line through the points. All right, but I actually have a picture of this, so I'll just show that instead of me trying to draw it. Let's copy. All right, so this is what it's going to look like. So this is the graph of y equals 2 to the x. You can see that the coordinates here, these guys, -3, 1/8, -2, 1/4, they correspond exactly to our function table. Okay, so that's all you would do. You would plot these points and draw this kind of curve through the points. All right, so that's what an exponential looks like. All right, so any questions? Okay, so now let's look at one more. Let's look at when the base b is between 0 and 1. All right, so let's look at when b is between 0 and 1. Okay, and the example we'll look at very quickly is when the base is 1/2. Okay, so 1/2, so in this example, b is 1/2, and that's definitely in between 0 and 1. All right, so let's look at the graph of that guy. All right, so it's going to look a little different, actually. All right, so you can see that the shape of the graph is actually quite different than when the base was 2. All right. So I'm going to touch upon this later, but notice that when the base was 2, we have the graph in this increasing direction. As I travel out on the x-axis, the y values are getting larger. However, when the base is between 0 and 1, I have this decreasing shape. As I travel out on the x-axis, the y values are getting smaller. All right, so I hope we kind of see the difference in shape depending on what the base is. All right. All right, good. So let me just rattle off some properties of the exponential function. All right, so.
Is that graph like that for any numbers between 0 and 1?
Yes, when b
Right.
between 0 and 1, you're going to get this shape. Was that your question?
Yeah, thank you.
Okay, good. Good, good. All right, so let's just rattle, so let me just rattle off some properties of the exponential function. Just good things to know about it. So let's just write properties of f of x equals b to the x. All right. So by properties, I mean like where the asymptotes are, the domain, range, all those pieces of information about a function. All right. So firstly, I have written here it's 1-to-1. Okay, it's a 1-to-1 function. You can see that pretty easily from the graph because it passes the horizontal line test. All right, horizontal line test tests for 1-to-1-ness. All right, so you can see it definitely passes the horizontal line test, so it is 1-to-1. All right, good. Next, we have a horizontal asymptote. Horizontal asymptote. Where is it at? It's at the x-axis, which is the same as the line y equals 0. Okay, good. Domain. So what x values are permissible to plug into this function? Are there any restrictions? Are there any bad numbers that would cause problems in this exponential? No. You can raise b to any power you want. Any number will be fine. So the domain will be -infinity to infinity. All right. So there's no issues. There's no domain restrictions. It's a very nice function. All right. The range. What are the y values that come out of this guy? Well, you can look actually. If you look at the graph, you get y values from 0 up to infinity. Okay, you don't ever land in the third and fourth quadrant, so the y values are not negative. All right, so the range is just going to be 0 to infinity. All right. All right, a few more. Y-intercept is, that's going to be 0, 1. How do I get that? Well, you just plug in x equals 0 into your function. All right, if you plug in x equals 0, you get b to the 0th power, which is always 1. That's why this coordinate pair is on the graph. And then this is what was asked before. The graph is increasing if b is greater than 1, and just intuitively that means the shape is going to look like that. Okay, so that's just like an intuitive picture of what it means for a function to be increasing and then decreasing if b is between 0 and 1. All right, and again, the intuitive picture is that it's going to look like this. All right, so these are not the rigorous definitions of increasing and decreasing functions, but the picture explains it really well. All right.
When you say decreasing, what what exactly do you mean by that one? Like when you say it's decreasing, like you mean like the graph is decreasing?
Okay, so decreasing rigorously means if I make the x values larger, the y values get smaller.
Okay.
So it's an indirect correlation. If I make x bigger, y gets smaller.
Got it.
Okay, and let me just write that in symbols. So it means that if x is greater than y, this will imply that f of x is less than f of y. All right, so notice this sign shift. Notice the inequality flipped. If x is greater than y, if I make x bigger than y, the function evaluated at x will be smaller than f evaluated at y. Right, so this is kind of like the symbolic representation. All right, so that's what it means to be decreasing right here, this implication. All right, and then I guess just for the sake of completeness, what is this for increasing? Well, if x is greater than y, then the inequality is preserved. If x is greater than y, then f of x is also greater than f of y. Okay, so that's what increasing means. All right, so what I have written here is just compare increasing, decreasing between 2 to the x and 1/2 to the x. So look at the graph for 2 to the x. It is increasing because the base is bigger than 1. Go to the graph for 1/2 to the x. It is decreasing because the base is between 0 and 1. All right. So that's pretty much that. Okay. So that's a nice crash course in the exponential function. All right, good. So now that we know what the exponential looks like, so this is kind of the so-called toolkit function or parent function that we're going to transform, we can look at transformations, all right, because that's what we like to do. So transformations of, so b to the x, all right, so b to the x is playing the role now of our toolkit or parent function, all right? This is the thing that we're going to apply vertical shifts to, horizontal shifts, and whatnot, all right? Okay, so what do I have here? Okay, good. So I actually have a question for you guys. So firstly, let's consider this function. F of x is equal to 2 to the x plus 3. All right, and my question to you guys is what transformation of b to the x is this? Like graphically or geometrically, what was done to b to the x to get this guy?
Vertical shift?
Yes, it is a vertical shift. And would you like to maybe be a little more specific?
3 units up.
Yes, exactly. Perfect. So this is a vertical shift up 3 units. Excellent. All right, so just like we've been doing with everything else, with our functions and doing like, on the last exam we had transformations, we can also transform the exponential. Why not? It's a function, so of course it can be transformed. All right, so this is a vertical shift up 3 units. Very good. All right. All right, yeah, so now I just have another picture to show you guys. Yeah, so here I just have various vertical shifts of the exponential. Excuse me. I just have various vertical shifts of 2 to the x. So look, this blue curve is 2 to the x plus 3. The orange one is the parent function. It's just 2 to the x with no transformations. And then we have the minus 3, which is, of course, vertical shift down 3 units. All right, so I hope everyone sees, the plus 3 just brings it up 3. The minus 3 brings it down 3. All right, so nothing new here. We're just applying our transformations to the specific case when the function is 2 to the x. Okay, so all of our rules still apply from earlier. All right, so there are some, so the properties of the function do change though when you do a vertical shift. So like the horizontal asymptote changes and the range changes. All right, so notice now the horizontal asymptote is, okay, so look at 2 to the x plus 3. We do have a horizontal asymptote not at y equals 0, but now at y equals 3. All right, so that's at y equals 3. The range is no longer 0 to infinity. It's now 3 to infinity. All right, so that's another thing that changed. And the y-intercept also changed. The y-intercept is 0, 4. Okay, as opposed to 0, 1. All right, so that's what changed here. All right, so now let's just like jump to the general case. All right, so this was like a specific transformation. Let's just see what it looks like in general.
Could you explain why the oh, that's the range. I'm sorry. No. Yeah. So could you explain why 3 is included as part of the range, like not included?
3 is not included. Are you asking why it's not
Yeah.
included? So 3 is not included. So if 3 were included, that would mean that 2 to the x would have to be 0 for some x value. Right? So if the function actually achieved the value of 3, do you agree that this term would need to be 0?
Yes.
However, an exponential function is never 0. 2 to some power will never be 0. So you're never going to actually achieve the value of 3. Right?
Got it.
Yeah. So that's the same reason why the range of the normal exponential is 0 to infinity. It's never going to be 0. Okay.
Yeah.
Dumb question, just out of curiosity. What if our function is 0? So like 0 to the whatever power. Our base is 0.
Yeah. So let me think.
Well, it wouldn't be a function because it would just equal 0 actually, right?
Yes. So I'm trying to think. So there are some problems with 0, like 0. So like in calculus, you'll talk about this, but pretty much like 0 to the 0 is undefined. There's no way to meaningfully assign that as a value. So you will run into trouble if you use 0 as a base. Yeah. Sorry, I don't have too much of a satisfying answer for that. But like you do run into some troubles with that. Yeah.
Got it. Thank you.
Good. So just now let's just do a transformation in general. So in general, a transformation of b to the x. What does it look like? So it'll look like this. Will be f of x equals, so we have a times b to the x plus c plus d. So hopefully this looks kind of familiar to when we were doing transformations of other functions. All right. So let me tell you what these letters are. So A is the vertical stretch or compression. Okay. Good. How about C? What does that x plus c mean in the exponent there? So notice that how the input x is being added to. So recall from our earlier work that will correspond to a horizontal shift. Okay, so C is horizontal shift. All right, so nothing really new going on here. We're just applying our old rules of transformations to the specific case of the exponential function. All right, so this is actually kind of a review. You can think of it like that. Good, and then the plus d, that will be a vertical shift. Okay, vertical shift. All right, so this is what a transformation will look like in general.
There's no horizontal compression because of the asymptote?
That's a great question. So you don't need to worry about horizontal compressions, and I will tell you why. So horizontal compression, you multiply the input by a number. So for instance, do you agree that b to the 3x would be a horizontal compression?
Yes.
But by properties of exponents, this is the same as b to the 3rd to the x. So all I've done is just change the base to a new number. So it's like b to the 3rd raised to the x power. So you don't really need to worry about horizontal compression because all it does, it just changes the base.
Gotcha.
Okay. But very good question. All right. Good. Now let me just quickly say the properties of the general guy. All right. So properties of like what are its domain, range, and asymptotes. So now let's just look at properties of the transformation. A, b to the x plus c plus d. Okay. What are the properties of this guy? All right. Nothing too crazy. So it's going to be a horizontal asymptote.
Do reflections, I'm sorry to interrupt though, but
It's okay.
do reflections also count or no? It's because of that rule that it cannot be a negative number.
You could also do reflections. That will, so a reflection about the x-axis will be encoded into the vertical stretch or compression.
Okay.
Because if a is negative, like -3, you would stretch by 3 and then reflect.
Okay.
But if you do like a b to the -x, so that would be a reflection about the y-axis, well, again, use your properties of exponents. You're just changing the base.
Mm-hmm.
So you don't need to worry too much about horizontal things because it just gets absorbed into the base. So that's a nice thing about these exponentials.
If you're doing a reflection over the x-axis for the a value, can you do the same as you did for the last time? Like you can reflect first and then vertical stretch, or stretch first and vertical?
Yes, absolutely. Reflections and stretches in the same direction, meaning stretch and vertical stretch and reflection can be done in either order.
Okay.
All of our rules from the last few classes, they still apply. We're just looking at a specific case of that. Good, good. All right, so where was I? Yeah, so I'm just listing the properties of the transformation. All right, horizontal asymptote at y equals d. Domain, again, all real numbers. It's going to be minus infinity to positive infinity. All right, so just note that no x values are going to create a problem in this function. You can raise b to any number. There's not going to be any problems there. All right, but the range does get shifted. So this vertical shift of plus d, that will change the range from d to infinity. All right. All right, how about y-intercept? All right, so just recall, to find the y-intercept, you just have to plug in x equals 0. Okay, so what do you get there? You get y is equal to a times b to the 0 plus c plus d. And that's just a, b to the c plus d. So you get a y-intercept at the coordinate pair 0, comma, a, b to the c plus d. All right. I know this looks very abstract because I'm just dealing with these letters, but it will come to life when we do a concrete example. All right. Yeah, so those are all the important properties. Okay. All right, what do we got? What do we got? Right, okay, good. So I'm just going to do one example of a transformation.
Does the same apply to finding the x-intercept?
X-intercept. Right, so x-intercept is when the y value is 0. So you will need to solve an equation. You would need to set the function equal to 0 and solve. That will not always be possible. It depends on what transformations you have done. Okay, so the example I have here, the example is f of x equals 2 to the x plus 1 minus 3. And what I will ask is a few things. State the transformation. So state the transformation 2b to the x. So what's being applied? Give me the domain, range, and y-intercept, and horizontal asymptote. All right. All right, so this is kind of how a question will look about these transformations. I'm going to give you a function. It's going to be some transformation of a parent function, and just kind of tell me these data points. All right, so state the transformation. So would someone like to tell me what transformations am I applying to 2 to the x? So actually, let me change it. It's a transformation to 2 to the x. So the first thing, state the transformation. So would someone like to tell me what am I doing to 2 to the x to get this guy geometrically?
Isn't it a vertical shift down 3? And then, sorry, 1 second. And then a horizontal shift left 1.
Exactly. Perfect. Thank you. Vertical shift down 3 and horizontal shift left 1. And let me just explain quickly how I got these things. The minus 3 outside, the minus 3, that is precisely the vertical shift down 3. And the plus 1 to the input, you're adding 1 to the input of the function. We know that that corresponds to a horizontal shift left by 1. So the left is intimately related to the plus sign there. Okay. Plus 1 means left 1. Okay. Very good. Next, domain. Yeah, so the domain for all of these guys is always going to be all real numbers. And we notate that in interval notation as minus infinity to infinity. All right, the range. So the range is just going to, you need to look at the vertical shift. You're going down 3, so the range will be minus 3 to infinity. That's how you do that. Okay, and y-intercept. So to find a y-intercept, you just need to plug in x equals 0. So let's do that. Okay, so I get y is equal to 2 to the 0 plus 1. I'm plugging in x equals 0, so I have 2 to the 0 plus 1 minus 3. This is the same as 2 to the first power minus 3, which is the same as 2 minus 3, which is the same as negative 1. All right. So I hope that's okay. Let me just clean these up a bit. Equals minus. Okay, so then so the y-intercept will be at 0, comma, negative 1. So it's the y value you get when plugging in x equals 0. All right, very good. And then the last thing will be the asymptote. So you're going to get a horizontal asymptote. Again, that's going to be related to, there's 2 ways to find it. You can just look at the range. It's going to be at this left endpoint of the interval, or you can just look at the vertical shift. Okay, so it's going to be at y equals minus 3. And that's it. So kind of the idea is, given this knowledge of the function, all of these characteristics, domain, range, y-intercept, horizontal asymptote, I would hope that it would be very easy to graph it, given all of this information. All right, so I will ask you guys to graph a few of these on the homework. All right? And it should be pretty easy to do so, given all of this information. Okay. All right. Good. So that will wrap it up for exponentials. All right. So any questions about anything?
Does it matter what order you do it in, the proper or the arithmetic?
So what do you mean by that? The order of what? The arithmetic?
The order of our transformations, like it did in functions.
Yes, it does matter, and it's going to follow the same order that I listed in whatever lecture that was.
Got it.
So that order that I specified, that applies to all functions. And we're just dealing with the specific function right now, so it's going to still hold. Yeah, everything we talked about is still valid. All right, very cool. All right, so we're actually going to do a real world application. All right, so I think this is maybe the first time we've done some sort of real world stuff. So maybe this is something you've seen in high school. So it's called the compound interest formula. All right. Compound interest formula. Okay. All right, good. So I just have some writing. So actually, I think I'm just going to type it like I did that one time, a little quicker. So let me see if I can do this. Okay, so what is the compound interest formula? All right, so I'm just going to type for a little bit. Just give me a second. All right, so this formula is used to determine the amount of money in some account after T years, okay, such as a mutual fund or retirement account. Okay. Now, what does the word compound mean? So compounding means that the interest is calculated with respect to the accumulated value of the account and not to the original amount. Okay. So pretty much when you calculate that interest, the quantity you use in that calculation is the present value of the account, not the original value that was in that account when you opened it up. All right. All right, so this is just like a brief description of the formula. What is it used for? What is the formula? All right, so here we go. So the formula is, it's A of t equals capital P multiplied by 1 plus r over n to the n times t power. All right, and of course I have to tell you what these letters mean. So firstly, so we need to talk about the input of the function. The input is t. So what is t? T will be number of years. So t is number of years. Okay, that's the input. Now, what does the function output? A of t, that's the output of the function after you plug in a number t. Well, A of t will be how much money you have in your account after t years. All right, so A of t, so just said a little more formally, A of t is your account value after t years. All right, so if I plug in like 3, A of 3 will tell me how much money I have in my account after 3 years have gone by. Okay, all right, so we just have a few more letters to talk about. What's capital P? P is the starting amount in the account. How much do I initially put into this account? So P is the starting amount in the account. Okay, and it's also called the principal. All right, so that's just another word for it. It's also called the principal. Okay, good. So just 2 more things to identify here. R is the annual percentage rate. R is the annual percentage rate, and that's usually written as an acronym as APR. So I've seen this acronym be used in like car commercials and stuff, like, oh, it has a low APR. I was like, oh, okay, so that's what that means. So it's your annual percentage rate, or APR, in decimal form. Okay, so you have to convert that percentage into a decimal. Okay. And then finally, N is your number of years, number of times you're compounding in 1 year. N is number of times you're compounding in 1 year. 1 year. All right. So just recall that compounding means you're adding interest to the account, and you're doing that, the calculation you're doing for that interest, you're using the present value of the account, not the original amount. Right. All right, so let's use this. Let's use this formula. All right, so let's do a word problem. All right, so I'm just going to type again just to make things a little easier. So this will be a nice application. So EX, for example. So here it is. So we deposit $3,000 in a bank account, which earns 3% interest, which earns 3% interest compounded quarterly. All right, and the question is, how much money will be in your account after 10 years? All right, so that's what this formula is useful for. It will tell you how much money you will have given some conditions in a certain number of years. All right, so let's use the formula. So for the formula, we need a few pieces of data. We need P, R, N, and T. P, R, N, and T. So let's list what each of those things are. So here, P equals what? Okay, so P is the amount of money that you deposit into the account initially. It's how much you put in at the start. So that's going to be 3,000 in this case. 3,000. All right. R is going to be your interest rate, but in decimal form. Okay, so I haven't gone over this, but to convert from percentage to decimal, you just need to move 2 places to the left, okay? Or you divide by 100. So it will be 0.03. All right, so I hope that's okay, converting percentage to decimal. You just have to move 2 to the left, okay? And you put the decimal point there, and it will be 0.03, okay? Oops. Good. And how many times are we compounding per year? N equals what? Okay, so it's a little tricky wording. We're compounding quarterly. That means we're compounding 4 times per year. N equals 4 since we're compounding quarterly. Okay, good. And finally, T. So T is how much time we would like to pass and see how much money is in the account after that time. So T will be 10. All right, because we're looking for how much money is in this account after 10 years. All right, good. Finally, we can plug in to the formula. So plug in. Plug in. All right, good. So I'm just going to write the formula in general. A of T is equal to big capital P multiplied by 1 plus R over N to the N-th power. Good. Now let me just substitute all of our values in for these letters. So P I will replace with 3,000 multiplied by 1 plus R over N. R is 0.03. Okay, so I'm putting that here. N is 4, so let me put 0.03 over 4. And this will be to the N-th power, N times T. So N is 4 and T is 10. So it's going to be to the 4 times 10th power, AKA to the 40th power. Okay. Good, and with these questions, definitely use a calculator. And I will put a wavy equal sign to say it's approximately. It's not exactly equal to, but it's approximately. That's what the wavy equal signs mean. It will be 4,045.05. Okay. So that's really it. It's just an exercise in plugging in to a function. There will be a homework question on this. However, on the homework, you will be solving for P. I will give you A, R, N, and T, and I want you to find P. All right, so you'll see that on the homework. It'll be slightly different. Okay, the homework, you're gonna have to solve for P. But that shouldn't be that bad. All right, so any questions on this compound interest formula? I think it can be pretty useful in the real world, so it's good to bring it up.
So to get P, just real quick, could we just do everything in the parentheses and then how would we go from there?
Right, so I'm gonna give you everything but P, right?
Yeah.
So you would have a number on the left side, which is equal to big P times another number here. So how do you solve for P? You just have to divide both sides by numbers. You see what I mean? So P will be number over numbers. I know that sounds kind of silly, but yeah, you're just going to have an expression just involving P times some number. You just have to isolate it by dividing both sides by what's ever here. Yeah, so it's just like algebra. Good. So that'll be on the homework, so just look out for that. I just wanted to give you guys a warning. On the homework, you'll be solving for P, not A of T. Right. All right, good. So we come to the final topic of the evening. Very important, very exciting applications all over mathematics, all over the real world. Just so insanely important. I can't even stress it enough. This is called the number E, okay? The number E, also referred to as Euler's number. So I'll just put that in parentheses. So Euler was a very famous mathematician. He was like a human calculator. He was just, you know, a beast. He was phenomenal. He has discovered some great things in math. So great that they named a number after him. Okay. All right, so that's, right. Okay, so how do we get the number E? Well, it's actually very related to the compound interest formula. All right, so it's another application of it, which is cool. So let me just say that very quickly. So I think I'm going to type again, if you guys don't mind. Okay, so how do we get the number E? So let me type and I'll explain. So the specific case of okay, so it's going to arise as a specific case of the compound interest formula, plugging in certain numbers into it, okay? So we let P be just $1, okay, invested at 100% interest. So AKA R will be 1. Okay, that's the decimal form of 100%. So R is 1. Okay, and how many years? We're just looking at it for 1 year. For 1 year. So in other words, T is 1 as well. Okay. Now there's going to be one thing varying. It's the number of compounds, with number of compounds N varying. Okay, so we're going to let N be the variable now. Everything else is fixed. R is 1, T is 1, and P is 1. Now we're just going to let N, the number of compounds per year, change. So this sentence is not complete yet. With number of compounds N varying is of utmost importance. Okay, so now let me write what this formula looks like with these specific variables. Okay, so it will be A is equal to, so P is 1, right? So that goes out in front. It was P multiplied by 1 plus. Okay, R is 1 as well. So I put 1 over, that R went here, it was 1 plus R over N. N, though, the number of compounds, we're not assigning a definitive value. That's what we're going to let vary now. That's going to be our variable. So 1 plus 1 over N. Okay, and this is raised to the nth power. This will be N times 1. All right, so I hope everyone can see this is a specific case of the compound interest formula with these parameters. R is 1, T is 1, P is 1, and we're letting the number of compounds stay as a variable. That will be N. Okay, good. And of course, I don't need this 1 times out front and the N times 1. So in other words, A is just 1 plus 1 over N to the nth power. Same thing. Okay, good. So we're getting there. We're getting there. So now we view this. So we view this as a function of n. A function of n. Okay, because I'm letting now the n variable, the number of compounds per year, I'm letting that vary. Everything else is fixed. Okay, and what we're going to look at is we're going to look at the behavior of this function as n gets larger and larger. We're going to let n tend to infinity and see what happens to this quantity.
Do we convert the 1 to a decimal form or no?
I did convert the 1 because it was 100% interest. And 100% converted to a decimal is 1.
Yeah, you're right.
Yeah, so the formula calls for the decimal form. That's why I did that. Okay, so as I was saying, let's view the behavior of this function. So as I want to let n, this number of compounds, get larger and larger. As n, so as n gets larger and larger. Okay. Yeah, so let's do that. I actually have a nice little demo thing, so let me go to that. All right, just give me a second. 1 second. Let me just go to my browser. Let me see where we at. Right, okay, good. Okay, awesome. So, no, don't want that. Hold on. Yes, that's what I want. Okay, good. So look at what I have here. This is precisely the expression that I want to look at. And I have this slider here that will control n as I let it get, I can vary n, and I can make it really big and really small. Okay, so just notice when n is 1, this expression is 2. So the output of the expression is right here. N is 2. So look at what happens to the output, this y equals thing, as I make n huge and huge. Maybe it's going to blast off to infinity. Maybe it's going to settle down to a number. Let's see what happens. All right, so I'm going to slowly make n bigger and bigger. So this quantity, 1 plus 1 over n to the nth power, like when n is like 1,570, it's still settling down to this. It's not growing like crazy. It's kind of settling down to this 2.7 thing, it looks like. All right, good. I'm going to keep going. Yeah, so I'm making n like pretty huge right now, and the output is staying kind of level. We're just hovering around this 2.71 area. And you can see that this is going to continue. All right, so I maxed it out at 5,000, and look, so this is this expression when n is 5,000. It's a pretty small number. It's just 2.718 and so on. Okay, so that's kind of interesting. Maybe you were expecting it to blast off to infinity or something like that, but no, it kind of stays settled down to this. And you could also see this with, sorry. You can also see this with the graph. So what I have graphed here is 1 plus 1 over x to the x. And you can see that as I let x get huge and huge, as I let x get larger and larger, it's getting a horizontal asymptote at that 2.71 value. All right, so you can just look at the y coordinate. It's going to slowly get closer and closer to that 2.7. Okay, so kind of just seen here that as I make n huge and huge, this quantity approaches this number, 2.718, and so on, and that number is actually E. Okay, so let me go back to the notes. Okay. Okay. Good, good. All right, so let me just quickly write down what we just observed with that quick demo. All right, so we see that as we make n larger and larger, the expression. So what expression were we looking at? It was this 1 plus 1 over n to the nth power thing. What happens? What's the behavior? What's the end behavior of this guy when n gets really large? This expression approximately becomes 2.718 and so on. So if you just remember from before when I made the slider up to 5,000, you saw the number 2.718 ... coming out. Okay, good. So we're now ready to state the formal definition of E. So, definition. So the number E is defined as the quantity that 1 plus 1 over n to the nth power approaches as n approaches infinity. Okay? So as you let n tend to infinity, as you let n get really, really, really big, this quantity, 1 plus 1 over n to the nth power, will approach some number, and that some number we call E. All right, so now let me just rephrase this in some other way. So in other words, this quantity, 1 plus 1 over n to the nth power, approaches E. So I hope you guys remember this notation from the n behavior of polynomials. In other words, 1 plus 1 over n to the nth power approaches E as n goes to infinity. Okay? So it's defined to be this limiting quantity that you get when you make n large and large. Or if you want to be even fancier, so you can also phrase this in the language of calculus using limits. This would be a limit as n goes to infinity of 1 plus 1 over n to the nth power. This is by definition E. Okay, so don't worry too much about this last one. This is just kind of just like things to come if you take calculus 1. All right, so really what I'm doing here is I'm taking a limit as n goes to infinity, and this is how you notate it. This is the symbols for how to represent a limit. All right, so you'll see this in calculus. All right, good. And now let me just end class with just a quick fact about E, and then we will call it a night. So what does E look like? Like what are the first few numbers of E in its decimal expansion? So E is approximately. So the way the equal sign means approximately. It is 2.718,282. Okay, so it's approximately this number and is irrational. Okay, so what that means to us, irrational means that the decimal expansion is infinitely long and follows no pattern.